A1 with 139 zeros after it. That is how long our vacuum is expected to last. The universe we live in is not in its lowest possible energy state. It is balanced on a ledge that quantum mechanics says will eventually give way. Is that balance permanent? Or is it a trap that fails with zero warning? Physicists call it vacuum decay. It is not a blast, and it is not a collapse. It is the vacuum switching states. The quantum field that allows atoms to form, molecules to bond, and stars to burn shifts into a lower energy configuration where none of those processes function. This is not a practical danger story. It is a forensic story about what the equations say about empty space. And the evidence comes from two numbers, both measured at the Large Hadron Collider at CERN. In 2012, physicists confirmed the Higgs boson at a mass of 125.20 giga-electron-volts, roughly 125 times the mass energy of a single proton. This measurement was one of the great achievements in modern physics, but it also delivered a verdict no one was hoping for. The Higgs field, the quantum field that gives mass to fundamental particles and holds the architecture of matter together, is not in its most stable possible state. Physicists call our current state a false vacuum. It is a metastable configuration. It has held for 13.8 billion years. The mathematics of the Standard Model say it will not hold forever. Somewhere in the equations of quantum field theory, there is a lower energy state the Higgs field could fall into. And if it does, everything we recognize as the physical universe would stop working. Whether the universe is permanent depends almost entirely on those two masses. The Higgs mass is 125.20 giga-electron-volts, plus or minus 0.11 giga-electron-volts. The top quark mass is 172.57 giga-electron-volts, plus or minus 0.29 giga-electron-volts. Both are the 2025 global averages from the Particle Data Group, combining data from the ATLAS and CMS experiments at CERN. These two numbers, and almost nothing else in the Standard Model, determine whether the universe is permanent. And the margin between permanent and temporary is extraordinarily thin. If the Higgs boson were just 2 giga-electron-volts heavier, 127 instead of 125, the universe would be absolutely stable. The Higgs field's internal stiffness would remain positive at every energy scale. The vacuum would never decay. Physics would persist for all of time. If the Higgs were 2 giga-electron-volts lighter, the expiration date would move dramatically closer. 2 giga-electron-volts. That is less than a 2% shift in the Higgs mass. That is the entire margin between a universe that lasts forever and one that does not. The Higgs landed almost exactly on the boundary, balanced on a measurement error. As of 2025, no published model has fully explained why. Steingasser noted in a dedicated analysis that the Higgs mass, its self-interaction strength, and its vacuum energy all appear tuned near critical phase values. Is it coincidence, selection, or a signal of unknown physics? That question is still open. The mechanism is settled. The top quark is responsible. It is the heaviest fundamental particle ever measured, and because it is so heavy, it pulls on the Higgs field harder than anything else in nature. At the energy scales of everyday matter, the Higgs field is stable. But as you push to higher and higher energies, the immense mass of the top quark drags the field stability downward. At roughly 10 to the power of 10 giga-electron-volts, that stability crosses zero. Above that scale, a deeper valley appears in the energy curve of the Higgs field. That deeper valley is the true vacuum. The state we currently occupy is the false one. In classical physics, a ball sitting in a valley with a barrier around it stays there forever unless something pushes it over. Quantum fields do not need a push. Through quantum tunneling, a microscopic region of the Higgs field can pass through the energy barrier spontaneously and land in the true vacuum without ever climbing over the top. This is not hypothetical. Quantum tunneling is measured routinely in nuclear decay, semiconductor junctions, and scanning tunneling microscopes. The same physics applies to the Higgs field. In 1980, Sidney Coleman and Frank De Luccia published the foundational calculation for how this process works in a gravitational setting. What they found is that the transition begins with a bubble. A region of space smaller than a proton tunnels into the true vacuum state, creating a tiny sphere operating under different physical constants. The space outside remains unchanged. Whether that bubble survives depends on a contest between two forces. The energy released by converting volume to true vacuum scales with the cube of the bubble's radius. The energy cost of maintaining the bubble wall scales with the square of the radius. For very small bubbles, surface tension wins and the bubble collapses back. But once the bubble exceeds a critical size, volume energy overwhelms the surface. The bubble begins to grow. And from that moment, nothing in physics can stop it. The wall accelerates outward. It approaches the speed of light asymptotically, meaning it gets closer and closer to light speed but never quite reaches it. And because no signal, no particle, no warning of any kind can travel faster than light, the bubble wall arrives at any point in space at essentially the same instant as any light that might have announced its existence. There is no advance warning, no detection window, no time to observe it approaching. If a vacuum decay bubble nucleated at Alpha Centauri, 4.24 light-years from Earth, we would have roughly 4 years and 3 months of existence remaining. We would not know it for a single second of that time. The first sign would be the wall itself, passing through our solar system and converting every particle it touched. If you came here for forensic physics and not clickbait, subscribe. This channel dissects the quiet ways the universe can end, one verified number at a time. What happens at the bubble wall is something no existing documentary has fully explained, and it answers a question that even researchers with doctoral degrees have raised in published discussions. As the wall sweeps through a region of space, the Higgs field shifts to its new value. Every fundamental particle acquires a different mass. For the quarks inside protons and neutrons, the change is extreme. The quarks become far heavier, but the strong nuclear force that binds them together does not scale the same way. That force can no longer contain the quarks. Protons disintegrate. Neutrons disintegrate. Every atomic nucleus comes apart. Not because something smashes it, but because the rules that held it together no longer apply. Matter does not simply break apart. Atoms stop being a meaningful concept. Inside the bubble, the fundamental constants of nature are rewritten. The electromagnetic and weak forces may merge. Molecular chemistry becomes a mathematical impossibility. No bonds, no structures, no complexity of any kind. If the true vacuum has negative energy density, and most standard model calculations indicate it does, the space inside the bubble does not merely operate under different rules. It curves inward and collapses, like a bowl caving in on itself. A gravitational implosion confined within the expanding wall. Coleman and De Luccia addressed this in their 1980 paper. They considered whether the new vacuum might support some form of structure, perhaps different from what we know, but still capable of complexity. Their conclusion was blunt. Any stoic comfort that the new vacuum might sustain some structure capable of knowing joy had been eliminated. That conclusion assumes the standard model is complete. Some physicists argue that undiscovered particles or forces could change the energy structure of the Higgs potential entirely. Supersymmetric partners, extra scalar fields, or gravitational corrections at the Planck scale might stabilize the vacuum. Others accept the standard model calculation at face value. If you had to bet on which explanation is right, coincidence, missing physics, or anthropic selection, drop it in the comments. In 1982, Edward Witten described a separate and even more extreme scenario. In certain theories with extra spatial dimensions, a bubble could form where space-time itself ceases to exist. Not a transition to different physics, but to nothing at all. That is called the bubble of nothing. It remains speculative, but it puts vacuum decay in context. A shift to different physical constants is the less extreme outcome. So how big is a 1 with 139 zeros compared to everything else? The universe is 13.8 billion years old. That is roughly 10 to the power of 10 years. Protons, according to grand unification theories, should last at least 10 to the power of 34 years. Current experiments at Super Kamiokande have not detected a single proton decay. The last supermassive black holes in the universe will evaporate through Hawking radiation in approximately 10 to the power of 100 years. That is the heat death. The timescale most people cite as the end of everything. The expected lifetime of our false vacuum, per a 2018 analysis by Andreassen, Frost, and Schwartz, is 10 to the power of 139 years. A 1 followed by 139 zeros. The vacuum outlasts the heat death. It outlasts the evaporation of every black hole. It outlasts every other physical process that has ever been calculated. The expiration date of the universe is so far in the future that the concept of future barely applies. If that timescale comparison reframed something for you, hit like. These numbers are worth seeing. The 95% confidence interval places the lower bound at 10 to the power of 58 years. Even the most aggressive estimate leaves trillions upon trillions of times the current age of the universe before decay becomes statistically expected. But the probability, however vanishingly small, is not zero. It applies per unit volume per unit time. A bubble could nucleate anywhere. The question is whether it could ever reach us. The answer depends on where it starts. The observable universe spans roughly 46 billion light-years in radius. The bubble wall travels at nearly light speed. The universe is expanding, and that expansion is accelerating. For a bubble that forms beyond a certain distance, cosmological expansion carries it away faster than it can grow toward us. The bubble never arrives. This means vacuum decay, even if it occurs, is not necessarily a universal event. Regions of true vacuum could already exist in distant parts of the cosmos right now, sealed behind the expansion horizon, permanently invisible and permanently irrelevant to our corner of the universe. We would never know. There would be no signal, no evidence, no way to confirm or deny it. There is a more immediate question. Could anything trigger vacuum decay locally? Could a particle collider produce enough energy to push the Higgs field over the barrier? The Large Hadron Collider operates at 14 tera-electron volts. That is the highest collision energy any human machine has achieved. But nature operates at vastly higher scales. On October 15, 1991, the Fly's Eye Cosmic Ray Detector in Utah recorded a single proton arriving from deep space with an energy of 3.2 times 10 to the power of 20 electron volts. Physicists named it the "Oh my God" particle. Its center of mass collision energy was roughly 2,900 tera-electron volts, more than 200 times the energy of the Large Hadron Collider. And that was a single event. Over 4.5 billion years, an estimated 3 times 10 to the power of 22 cosmic ray collisions have struck Earth at energies exceeding what the Large Hadron Collider produces. Across the entire observable universe, over 13.8 billion years, that number rises to at least 10 to the power of 50. That is more high-energy collisions than there are stars in the observable universe. 10 to the power of 50 natural experiments, each exceeding Large Hadron Collider energy, slamming into neutron stars, white dwarfs, planets, and interstellar gas. Not one has triggered vacuum decay. Not on Earth. Not anywhere in the observable universe. Do you find the cosmic ray argument reassuring? Or does it make the universe feel stranger, because it means the vacuum does not care what slams into it? This is the cosmic ray safety argument, first formalized by Scher and Zaglauer in 1988 and reinforced by the Large Hadron Collider Safety Assessment Group in 2008. If nature has been running this experiment for billions of years, across billions of galaxies, at energies no accelerator will ever match, and the vacuum has held, then no human experiment poses a credible risk. A 2025 survey by Stone and colleagues polled 20 physicists who specialize in vacuum stability. The average probability they assigned to the vacuum being definitively metastable was 45.6%. Only 18.8% believed that even a Type 3 civilization, one capturing the full energy output of a galaxy, could artificially induce the transition. The vacuum appears safe from external triggers. It will decay on its own terms, or not at all. So where does that leave us? The universe is metastable. That is what the Standard Model says, given current measurements. The Higgs field sits in a false vacuum that has lasted 13.8 billion years, and it will persist, by the best calculation available, for 10 to the 139 years. No known process can accelerate the transition. No instrument can detect an approaching bubble. If it ever begins, it will arrive at the speed of light, converting everything in its path to a state where atoms cannot form and chemistry cannot exist. But the fact that the universe is metastable may not be a defect. Some physicists have proposed that only a metastable vacuum allows the kind of complexity that produces observers. A 2025 paper by Steingasser and colleagues suggested that the instability scale of 10 to the 10 giga-electron-volts may actually explain why the Higgs mass is 125 giga-electron-volts and not some other value. If their model is correct, the near criticality of the Higgs is not a flaw. It is a requirement for a universe complex enough to ask the question. The universe is temporary, that is what the numbers say. But it is temporary on a timescale so vast that it outlasts the death of every star, the decay of every proton, and the evaporation of every black hole. We exist in the window, the brief, improbable window where the false vacuum holds, where the constants of nature allow atoms to bond and chemistry to function. That window has been open for 13.8 billion years. The math says it has at least 10 to the 139 years remaining, and in all that time, the vacuum has never once flinched. The next video in this series covers the full timeline of the far future, from 1,000 years to 1 quadrillion years. If a 1 followed by 139 zeros surprised you, wait until you see what happens to the universe between now and the final black hole. Which number from this video broke your brain? The 139 zeros, the 2 giga-electron-volt margin, or the 10 to the 50 cosmic ray experiments? Drop it below. If you are watching this series for the physics and not the panic, subscribe. Abyssal Cosmos goes deeper, one verified number at a time.